Okay, now let us look at functions of three or more variables. Um, so just in the same way as for functions of two variables, so if we have three variables, then the domain of our function is a subset of the 3D space. Then a function is a rule that assigns a unique output for every input. It's just that the difference is that now the input is a triple of real numbers rather than a couple of real numbers, right? And then we have f of x, y, z. Maybe we can write w equals f of x, y, z. Then x, y, and z are independent variables, and w is a dependent variable. So and so on and so forth, right? So everything is very, very similar. Now here is some example how we can compute the function of a function of several variables. So at the same time, it's going to be some good excuse to look at the max function. Now, so how does this work? So the function is the maximum um, of what? Of three numbers. So here, so x is 10, y is 5, and z is 9. So the maximum of x minus y. So we need to replace x with 10 and y with 5. 10 minus 5. Okay, so the second entry is 3y minus z. So 3 times y is 5 minus z is minus 9. And the third entry of the maximum is absolute value of x, which is 10 minus 2 times z, and z is 9. Okay, so let us compute this. So first let us compute all the three inputs of the maximum. So 10 minus 5 is 5. 3 times 15, 3 times 5 is 15. Okay, I'm going to just write 15 minus 9. And here we have the absolute value of 10 minus 18. Right. Okay, now let me just try this. So 18 minus 9, sorry, 15 minus 9 is 6. And 10 minus 18 is negative 8, right? So what we get is the maximum of 5, 6. And well, the third argument is absolute value of negative 8. And the absolute value of negative 8 is just 8. So this is the largest of the three numbers, 5, 6, and 8. So the largest of them is 8. So this is how we compute the value of this function. And well, this is just the printed version of the same thing. All right, how about level surfaces of 3D functions in general? So now it is a bit tricky to visualize a whole bunch of level surfaces if you have functions of three variables, not speaking of the graph of a function of three variables, because the graph of a function of three variables would be something like a hypersurface in a hyperspace. So I don't think that we can really realistically visualize it, right? So but sometimes it is possible to use, well, Wolfram Alpha and GeoGebra to do it. So let me show you how it works in Wolfram Alpha first. So x squared, so plus y squared plus z squared. Let's say first I'm going to try to draw a simple sphere, right? So and you can look at the sphere, but it will do even more complex surfaces. For example, I don't know. I'm going to add x, so x squared plus y squared plus x times z squared is 1, right? So this is the a level surface of the function x squared plus y squared plus xz squared. And you can see that, okay, Wolfram Alpha somewhat plots it, so you can look like, well, it looks like, I guess, like a knee or something like that. So another tool that is less powerful but does a better job in visualization is called GeoGebra, right? So in GeoGebra, so let me erase this. So if you want x squared plus y squared plus z squared is 1, it'll draw this sphere. But if you add x times it, I don't think it will draw it. Yeah, I don't think it's possible. um, to sketch something more complicated. Um, it is possible. I mean, it will do, I guess, something like minus y squared is 1, so that will do. So below it. And but GeoGebra is kind of does a better job at visualization than Wolfram Alpha. So sometimes I guess these tools could be helpful. All right. Now let me go through a simple example. So consider this function, and we're going to find two level surfaces. So the first level surface is going to be the one corresponding to the constant value of 9. So what is that? So to solve A, um, I'm going to rewrite my function x minus 1 squared plus y squared plus z squared, and should be equal to 9, right? And you see that the left hand side looks like the equation of a sphere. So 9 is 3 squared. So this is a sphere of radius 3 centered at the point 1. So here y squared is essentially y minus 0 squared. So 0 and 0 here. Right? So this is a sphere centered at this point, and its radius is 3. So if you want to plot it in GeoGebra, you can to look at it from, I don't know, different angles. So let me just erase this. Um, x minus 1 squared plus y squared plus z squared is 9. Somehow the first hyperboloid did not disappear. Okay, now it's just a sphere. Right, so you see that the center point is 1 0 0. So this is somewhere here. You can rotate it and look at it from different angles. Okay, now, so that was the first part. In the second part, the question is to find the level surface corresponding to a certain point, right? So the point is, so in part B, the question is to find the level surface corresponding to the point 1, negative 2, 3, right? So we want to find the level surface such that at the given point belongs to, right? So which means that if we substitute 1 for x, negative 2 for y, and 3 for z, then we're going to get a correct equation, right? So 1 minus 1 squared, so I have substituted 1 for x, plus negative 2 squared, now negative 2 for y, plus 3 squared, this should be equal to c. Right, so c is what? Is 0, plus negative 2 squared is 4, 3 squared is 9, so which is 13. So thus, in part B, our level surface is x minus 1 squared plus y squared plus z squared is 13. Well, this is still a sphere because of the same reason, with the same center. The only difference is that now radius is square root of 13. And if you want to plot it in GeoGebra, what you do is you just change this 9 to 13, and that's your level surface. Okay, I hope this is clear. Um, Now, this could go on forever. So we could talk about functions of 4, 5, and so on, of more variables. Of course, if we have a function of n variables, it is hardly possible to visualize it as a level set or a graph. It's just too many dimensions. So you can think of it just as an abstract device whose input is, a lot of numbers and whose output is just one number. So that's basically how it works. And here is a simple example. So if you have different ingredients in making a food product, then in order to compute the cost per unit, so you just add costs for all the products together, multiply um, by the quantities of um, all of the ingredients, and then you get the resulting cost of the resulting product. All right, so that's the end of this part. So please do the quiz. That'll help you to basically understand better what's going on here.